Hello, and welcome back to Discrete Mathematics. This is Lesson 13, an introduction to combinatorics. So what is combinatorics? It's the branch of math dealing with combinations of objects belonging to a finite set in accordance with certain constraints. Typically, at least in discrete math, it's dealt with counting. So counting is normally pretty simple, but we can find out pretty soon that it'll be a little bit more challenging than you might think. And it's typically used in a bunch of mathematical fields like probability, cryptography, set theory, graph theory, number theory, and more, especially computer science related ones like graph theory and cryptography. So there are a number of ways of counting, and these are the ones we're going to be discussing today. We're going to be reviewing the multiplication principle, and then we're going to be talking about arrangements with and without repetition, and we're going to be talking about permutations with and without repetition, and combinations with and without repetition. So let's get started. Okay, so the multiplication principle is probably a review. It's also known as the fundamental principle of counting because it's used in all of the following principles that I'll be discussing. So it basically says that if there are A ways of doing something and there are B ways of doing another thing, and they're going to be A times B ways of performing both actions. So, simple example here, just to get you familiar. There are 5 shirts and 3 pairs of pants. How many outfits are possible? Well, it's just going to be their product, 5 times 3, which gives us 15. So the next pattern that would naturally follow is the arrangement with repetition. And this is probably the simplest combinatorial pattern following our knowledge of the multiplication principle. And it's basically a way of arranging n options k times with repetition. So we would have n options for the first choice, n options for the second choice, etc., repeated k times. This would lead us with n to the k as our equation, or as our formula. So here's a quick example. How many binary strings are there of length 5? Well, there's going to be 2 to the 5 since there are 2 options for each character. We'd either have a 0 or a 1 in each spot. So that gives us 2 to the 5th. Right, that'd be 2 times 2 times 2 times 2 times 2 is 2 to the 5th. Similarly, how many 10-letter lowercase strings exist? Well, that's going to be 26 to the 10, because there's 26 letters for each option, and there's going to be 10 options total, giving us 26 to the 10. So the next simplest is going to be permutation without repetition, and this is going to be the number of rankings of a set of n items. So another way for we can say rankings is the number of orderings. So order does matter in this case. So we would have n options for the first choice, n minus 1 options since one option was already used over here, and minus 2 options for the third because an option has already been used here, an option has already been used here, etc., all the way down to 1, which gives us our formula for n factorial. So how many ways can 7 people be arranged in a line? The answer would be 7 factorial. So we have 7 options for the first person, 6 for the second because 1's already been selected for the first, and so on. Second example would be how many possible outcomes are possible for a race of 8 people. The answer would be 8 factorial. There's 8 options for first place, 7 options for second, etc. Next we have arrangement without repetition. This is commonly known as just permutation. That's how you might have heard of it before. This is just another way of saying it. This is the number of ways to arrange k items from a set of n distinct items. So they're going to all be different. And this is going to be very similar to the concept we covered before. We're going to have n options for the first choice and minus 1 options for the second choice. But instead of going to 1, we're going to stop just before so we can get k items total. And that leads us to this formula here. which is just a simplification of the algebra. So an example of this would be how many batting lineups of 9 people can be made from 15 players? The answer would be the permutation of 15 and 9, which would be 15 times 14, etc., all the way down to 7, which is the same as 15 factorial over 6 factorial, or this much right here, like 1.8 billion. So the next is going to be combination without repetition, and this is simply known as combination. This is going to be the number of subsets of k items from a set of n distinct items. And this is going to be represented as follows. It can be seen as C of nk, or it can be n choose k. This is probably the most common notation possible. And then here is the formula in general. It's going to be n factorial over n minus k factorial over k factorial as well. And you might notice that the only difference between this and the permutation formula is division by k factorial. So this is another way we can represent it as well. So a quick example, how many samples of 4 transistors can we make from a set of 40? And the answer is 40 choose 4, which is going to give us this number right here. So next is going to be permutation with repetition. And it's going to be the number of n items of types A1, A2, etc., all the way up to AK, with all the AIs adding up to n. So each one of these categories has to add up. Adds up to n. So we could first represent that using our combination tool that we just discovered before. Out of n choices, we would choose A1. And then since we've already chosen A1 choices, our new total would be n minus A1, choose A2, because that's the next category. And then following that, we're going to have n minus A1 minus A2, because we've already used them. Since we've already chosen those over here, then we choose A3, etc., all the way until we're down to our last category, and this always evaluates down to 1. And if we simplify the algebra down a bit, we'll get this formula in general, but however, both of these can be used equivalently. So, for example, how many 5-letter strings can be made from the letters in level? As you can see, there's 2 L's right here, 2 E's, and 1 V. So there's 5 letters total, which will give us 5 factorial over 2 factorial for the 2 L's, 2 factorial again for the 2 E's, and then 1 factorial for the 1 V, and that gives us 30. Next is going to be combination with repetition, and this is going to be the number of subsets of k items that can be of n different categories. So this is probably the hardest of the different types of combinatorial problems that we've seen so far. So it's often times called k multi-combinations or just multi-subset, and it can be expressed as n plus k minus 1, choose n minus 1, but by the symmetry of a combination, it can also be represented as n plus 1 minus 1, n plus k minus 1, choose k, and a common notation for it is just going to be n choose k with an extra set of parentheses around it. That's typically the notation for k multi-combination or multi-subset. Multi-choose also, and multi-choose k. So this might seem a little bit abstract, but hopefully this first example should clear it up a little bit. How many ways can we choose 5 cookies from 8 different types of cookies? Well, there's going to be, we're going to be taking a subset of 5 items, right? Because we're choosing 5 cookies. And we've got 8 total types, right? Whoa, yeah, that's a big arrow. Yeah, we have 8 total types. So we just plug in our numbers into the formula. This is k because that's the number of items in our subset. And then this 8 would be n because that's the number of categories. So that'll give us with 12 choose 7. And then in the next example, how many ways can 8 people leave an elevator going from floor 1 to floor 6 if everyone exits by the end? Well, in this case, our subset is going to be, the size of our subset is going to be 8, which will be our k, and then our n is going to be 6, since there's going to be 6 possible categories for people to assign themselves to, or 6 different floors for them to get off of. So if we plug in these values into our formula, we'll have 6 plus 8 minus 1, choose 6 minus 1, which is simply 13 choose 5. So this is just going to be another explanation of how this works and where that formula came from. Usually this isn't too important, but it's good background information. So the number of multi-subsets of size k is the number of non-negative integer solutions of the Diophantine equation x1 plus x2 all the way up to xn is equal to k for each xi in between 0 and k. So we can try to group each type of element by placing partitions down in between them. So here we have 9 circles, and we try to put bars down in between the circles to sort of partition them. But notice here how we have this double bar right here. That could lead to some ambiguity, because we could simply move it over here and it would look almost the same, but it would have it would have a different form. So these overlaps can lead to some ambiguity, so we need to come up with a different scheme, and our solution to this is to force each variable to be at least 1. So we just do a simple substitution, let y sub I equal x sub I plus 1, and if we do the algebra out right here, we'll have that y1 plus y2 all the way up to yn is equal to k plus n, because we add 1 n times, so it gives us this on the right hand side. So now we have k plus n minus 1 places to put n minus 1 partitions, which will give us the formula here. Since we're choosing n minus 1 partitions out of k plus n minus 1 locations. So that should be it. Thanks for watching. I'll be going over this more in the next video.